Imagine standing on the edge of a vast, silent crater, gazing up at a sky that's eternally black, dotted with stars that never twinkle. The ground beneath your feet is a fine, powdery dust that clings to everything it touches, and the air? Well, there is no air. This is the moon, our closest celestial neighbor, a place that has captivated humanity for millennia. It's been over 56 years since the first humans, Neil Armstrong and Buzz Aldrin, set foot on its surface during the Apollo 11 mission in 1969. They kicked up that iconic lunar dust, captured breathtaking photographs that would inspire generations, and planted the American flag as a symbol of human achievement. Since then, the moon hasn't been left alone. Dozens upon dozens of missions have revisited it, some gently landing to probe its secrets, others orbiting high above to map its rugged terrain, and a few even crashing deliberately to unearth hidden truths from the debris. It's the most explored, most scrutinized body in the solar system besides our own Earth. Yet, even after all these years of scrutiny, the moon guards its mysteries fiercely. We still don't fully grasp how it regulates its extreme temperatures, how it interacts with cosmic electricity, or why its soil behaves almost like a living entity, adhering to surfaces with an uncanny persistence. The more we delve into its depths, the more enigmas emerge, pulling us deeper into a cosmic puzzle that refuses to be solved easily. Some phenomena, like the moon's gravitational tug on Earth's oceans causing tides, or its precise alignment creating awe-inspiring solar eclipses, were deciphered centuries ago by brilliant minds like Galileo and Newton. But other aspects, stranger, more elusive ones, have only grown more perplexing as our technology has advanced, allowing us to peer closer than ever before. And one of those profound mysteries began with something deceptively simple, a faint chemical signal detected in lunar samples. It was just a whisper at first, a trace that hinted at the impossible. Then, another signal appeared, and another, from various missions using diverse techniques. Each one pointed toward the same astonishing revelation. Something was present on the moon that, by all conventional wisdom, shouldn't be there at all. What followed was a cascade of breakthroughs, rigorous experiments, heated debates, and frustrating contradictions that have kept scientists puzzled for over half a century. But stick with me through this journey, because by the end, you'll see how these discoveries aren't just rewriting our understanding of the moon. They're reshaping the future of human exploration in space. Science, as we all know, moves at its own deliberate pace, often frustratingly slow in the face of groundbreaking finds. You might assume that stumbling upon something utterly unexpected would ignite immediate revolutions in our knowledge, sparking headlines and paradigm shifts overnight. But reality is far more nuanced and patient. Sometimes, the most pivotal clues are buried in overlooked data, dismissed as anomalies, or even noticed by everyone but believed by no one due to entrenched beliefs. This is precisely the story that unfolded in 1976, when the Soviet Union's Luna 24 probe embarked on its historic journey. As the final chapter in a storied series of robotic sample return missions, Luna 24 didn't grab the front pages like its predecessors. It wasn't pioneering in scale or spectacle, but it quietly achieved something remarkable. The probe drilled approximately 2 meters into the lunar regolith, the loose, fragmented layer covering the moon's bedrock, extracting a slender core of soil and rock. This precious cargo, weighing a mere 170 grams, about the weight of a baseball, was rocketed back to Earth for analysis. And within that unassuming tube of extraterrestrial material, researchers uncovered something bizarre: traces of water, amounting to roughly 0.1% of the sample's composition in the form of H2O molecules. Even more intriguing, the water concentration increased with depth, suggesting it wasn't a superficial contaminant, but something embedded deeper in the lunar layers. This should have been a seismic moment in planetary science, a revelation that challenged the long-held view of the moon as a bone-dry wasteland. Instead, it was met with skepticism and dismissal. Experts attributed the water to earthly contamination, perhaps from the probe's mechanisms, the handling equipment, or even humidity in the labs back home. It was the convenient explanation, aligning with the textbooks that proclaimed the moon's aridity as fact. After all, the Apollo missions from 1969 to 1972 had returned samples showing similar faint hints of hydrogen-bearing compounds, possibly hydroxyl OH groups akin to water's building blocks. But those too were brushed aside as artifacts of contamination or instrumental errors, nothing worthy of upending established theories. For decades, these intriguing signals languished in obscure lab reports, footnotes in academic papers, and dusty archives. No dedicated follow-up missions were launched to probe deeper or verify the authenticity of these water traces. The prevailing assumption, that the moon was utterly devoid of water, held firm, stifling curiosity. It wasn't until the late 1990s and early 2000s that a reevaluation began, as new technologies and fresh perspectives cast those old data in a new light. What once seemed like mere noise started to resemble overlooked evidence of a wetter lunar history. But by then, precious time had been lost, years squandered ignoring clues that were staring us in the face. And when we finally mustered the resolve to return and investigate anew, the moon seemed to push back, revealing layers of complexity that defied our expectations. Picture this. If you could somehow transport yourself to the rim of certain craters near the moon's poles, you'd witness a sight that's almost otherworldly, not for what's visible, but for what's absent. No sunlight penetrates these depths, not even a glimmer. These are the permanently shadowed regions, PSRs, eternal voids where darkness has reigned for billions of years. This phenomenon arises from the moon's minimal axial tilt, just 1.5 degrees, meaning sunlight grazes the polar surfaces at shallow angles, never reaching the floors of deep craters. Temperatures in these PSRs plunge to below -240 degrees Celsius, -400 degrees Fahrenheit, colder than the surfaces of distant Pluto or the icy giants Uranus and Neptune. Such frigid conditions could theoretically preserve water ice indefinitely, provided it arrived via cometary impacts or other cosmic deliveries over eons. By the 1990s, this hypothesis gained traction. Perhaps the moon wasn't entirely parched. Maybe it harbored water ice in these cryogenic traps. Comets and asteroids, known to carry water, have bombarded the moon throughout history, and volatile materials from those strikes could migrate to the poles, freezing solid in the shadows. This idea ignited excitement not just for its scientific merit, explaining water's origins in the solar system, but for its practical implications. Lunar ice could transform the moon from a barren relic into a vital resource hub, a source of drinking water, breathable oxygen, and rocket fuel for future missions. Suddenly, the polar regions became the epicenter of lunar exploration. No longer content with distant observations, space agencies aimed to peer inside these enigmatic shadows. However, challenges abounded. The terrain is treacherous, illumination non-existent, and solar power unreliable in perpetual night. Yet the stakes were too high to ignore. If ice existed in exploitable quantities, it could revolutionize space travel. Thus, a flurry of missions targeted these poles, each seeking definitive proof. And that's where the moon's peculiarities resurfaced, turning what seemed like a straightforward quest into a labyrinth of surprises. As suspicions of polar ice grew, the initial strategy favored caution. Orbiters equipped with remote sensing instruments to scan from afar without the risks of landing. The pioneering effort was NASA's Clementine mission in 1994, a collaboration with the U.S. Department of Defense. Though not primarily designed for water hunting, Clementine mapped vast swaths of the lunar surface and identified permanently shadowed craters at the South Pole, bolstering the cold trap theory. However, it lacked the specialized tools to detect volatiles directly. That gap was addressed in 1998 with NASA's Lunar Prospector, explicitly tasked with searching for water indicators. Using neutron spectroscopy, it measured particle interactions with the surface, revealing elevated hydrogen concentrations at both poles, particularly in shadowed areas. Estimates suggested 10 million to 300 million metric tons of water ice, enough to fill countless Olympic-sized swimming pools and potentially game-changing for space exploration. But here's the twist that kept scientists on their toes. Hydrogen signals alone don't equate to water ice. They could stem from hydroxyl in minerals or other compounds. Lunar Prospector's data was tantalizing but inconclusive. It hinted at possibilities without confirmation. Orbiters provided maps and directions, lighting up potential hotspots, but they couldn't touch, taste, or verify. The scientific community was left in limbo, strong evidence, yet no certainty. The moon was teasing us, offering glimpses of its secrets while withholding the full truth. To break this stalemate, agencies pivoted to bolder tactics. If gentle orbiting wouldn't suffice, perhaps a more forceful approach could dislodge the answers. Enter the era of intentional impacts, crashing probes into the moon to analyze the resulting plumes. It might sound brute force, but the rationale was elegant. A collision in a shadowed crater could eject buried materials into sunlight, where orbiting or Earth-based sensors could scrutinize them. Lunar Prospector itself ended its mission this way in 1999, steered into a south polar crater. Hopes were high for detecting water in the debris, but telescopes saw nothing conclusive, perhaps due to impact angle or instrument limitations. A decade later, Japan's Kaguya orbiter followed suit in 2009, crashing after a successful mapping phase. But again, no definitive water signatures emerged, just more dust and ambiguity. Undeterred, NASA launched the Lunar Crater Observation and Sensing Satellite, LCROSS, in 2009, engineered specifically to resolve the water debate. LCROSS didn't impact solo. It trailed the spent upper stage of its launch rocket, which slammed into Cabeus Crater near the South Pole. Minutes later, LCROSS flew through the ejecta plume, its instruments sniffing for volatiles. This time, success. Water vapor was detected, along with hydrogen, carbon monoxide, ammonia, and methane, irrefutable evidence of water ice in a shadowed crater. The discovery electrified the world, dominating headlines and validating years of speculation. For a fleeting moment, the mystery seemed cracked wide open, but questions lingered. How much ice? Was it uniform or patchy? Ancient or fresh? And crucially, extractable? LCROSS provided proof, but at the cost of its own destruction. No follow-ups, no exploration. It confirmed water in one location, but left the broader picture murky. As we move forward in this tale, you'll see how this sparked a new generation of missions, more sophisticated and deliberate, probing not just for presence, but for practicality. And just when we thought we had it figured out, the moon threw another curveball. For years, the narrative centered on polar shadows as water's sole refuge. But then, orbiters like NASA's Lunar Reconnaissance Orbiter, LRO, operational since 2009, and India's Chandrayaan-1 began detecting hydroxyl and water molecules on sunlit surfaces, far from the cold traps. These signals weren't confined. They spanned the globe, albeit in trace amounts. Astonishingly, they fluctuated with the lunar day, weakening at noon under peak heat and strengthening as temperatures dropped toward evening. It evoked a bizarre lunar water cycle, where molecules migrated or reformed daily, driven by solar heating rather than earthly weather. Theories abound for this phenomenon. Micrometeorite impacts could liberate or deliver water from minerals. Solar wind, streams of charged particles from the sun, might implant hydrogen into oxygen-rich regolith, forming hydroxyl that evolves into water. Regardless of origin, this revelation shattered assumptions. The moon's surface wasn't uniformly dry. Water traces were ubiquitous. This broadened exploration horizons. Potential sites weren't limited to poles. Equatorial regions might yield resources too. If we could harvest these molecules, bases could sprout anywhere. This shift fueled the next phase, landers and rovers to ground truth orbital data. And in 2023, India's Chandrayaan-3 mission took center stage, aiming for the South Pole to confirm ice up close. Vikram lander and Pragyan rover touched down successfully, marking India as the first nation at this latitude. Equipped with spectrometers, Pragyan scanned regolith, but found no hydrogen, no water. Elements like aluminum, iron, and sulfur abounded, but the expected volatiles were absent. This paradox deepened the mystery. Why dry when orbitals screamed wet? Perhaps the water lurked deeper, beyond the rover's reach. As lunar night fell, both craft powered down, never reviving. But Chandrayaan-3 offered another gem, temperature data from its probe, revealing lunar soil's superb insulation. Surface heat dropped dramatically just centimeters down, suggesting ice could hide beneath a protective dust layer. This aligned with historical hints. Water increasing with depth in Apollo and Luna samples. Maybe we'd been skimming the surface, literally. If so, future tools need deeper drills. Fast forward to today, August 2025, and the quest intensifies. China's Chang'e 5 mission in 2020 returned near-side samples, but 2024 analyses revealed molecular water, H2O, in them, the first physical confirmation. Then, Chang'e 6 in 2024 fetched far-side samples from the Apollo basin, showing an extremely dry mantle with minimal water, 1 to 1.5 micrograms per gram, yet providing clues on lunar evolution. In a breakthrough, Chinese scientists in August 2024 devised a method to extract water from lunar soil by heating it, producing large quantities, potentially revolutionary for in-situ resource utilization. 2024 to 2025 saw more action. Japan's SLIM landed precisely in January 2024, analyzing rocks for origins. Intuitive Machines' IM-1 landed February 2024 near the South Pole, carrying experiments, though not primarily water-focused. But IM-2, launched February 2025 as Athena, targeted Shackleton Ridge with NASA's Prime 1 drill and PLWS payload to probe regolith for water ice during its 10-day mission. Early data suggests promising hydrogen signals, though full analysis is ongoing. NASA's Lunar Trailblazer, launched February 2025 to map water globally, tragically lost contact in August 2025, ending prematurely, a setback, but its partial data hints at more extensive ice than thought. China's plans for Chang'e 7 in 2026 include a flying robot to scout far-side water. NASA's Artemis program presses on. Artemis 2, a crewed lunar flyby, is slated for early 2026. Artemis 3, the first crewed landing since 1972, targets mid-2027 at the South Pole for water prospecting. Despite Viper rover's 2024 cancellation, efforts redirect to commercial partners. These updates underscore the moon's evolving story. Water isn't just a curiosity, it's the key to sustainability. Extractable H2O means hydration, oxygen, and fuel, hydrogen-oxygen propulsion, from local sources, slashing costs. Launching from the moon's low gravity, 1/6 Earth's, is efficient, turning it into a cosmic gas station for Mars or beyond. Bases could recycle water in closed loops, even irrigate lunar farms. Geopolitically, controlling water sites grants leverage in space's new frontier. Yet ambiguities persist. Orbital hydrogen versus ground dryness, vanishing daily signals, no visible ice sheets. Perhaps water is diffusely spread, deeply buried, or bound in minerals, demanding advanced tech. Recent studies suggest millions of tons at poles and water everywhere, even equatorially. UH-led research in 2025 uses cosmic rays to detect buried ice, promising non-invasive mapping. As we stand on this precipice, the moon beckons with untapped potential. Each mission peels back layers, but mysteries endure. What if the next drill strikes a frozen vein, or reveals water's solar system origins? The answers could propel humanity starward. But to grasp the full impact, to see how this unlocks the cosmos, stay with me. The moon's secrets are unfolding, and the best is yet to come. Now, let's dive deeper into the historical context to appreciate how far we've come. The Apollo era, from 1969 to 1972, brought back 382 kilograms of lunar material, revolutionizing our view. Initial analyses deemed it dry, but re-examinations in the 2000s found hydrated minerals, hinting at internal water from the moon's formation 4.5 billion years ago. The moon likely formed from debris after a Mars-sized body collided with proto-Earth, inheriting some volatiles. But intense heat from this cataclysm should have vaporized water, yet traces remain. Volcanic glass beads and samples contain water, suggesting a wet interior once. This internal versus external debate rages. Was water primordial or delivered later by comets? Chang'e 6's dry mantle findings lean toward the latter, but far-side differences complicate it. Engaging you further, consider the engineering marvels. Drilling on the moon isn't like Earth. Regolith is abrasive, vacuum conditions cause outgassing, and low gravity affects stability. Prime 1 on IM2 aims to drill 1 meter, analyzing cuttings for water. Extraction tech, like China's heating method, uses ilmenite FeTiO3 to react with hydrogen, yielding water. Imagine lunar water factories powering habitats. But challenges loom: dust storms from electrostatic charging, radiation, temperature swings. Artemis habitats will test these, with inflatable modules and regolith 3D printing for shielding. To encourage you onward, ponder the broader implications. Lunar water could enable asteroid mining, providing fuel for deep space probes. It ties into exoplanet searches. Understanding lunar water informs habitability elsewhere. And ethically, who owns lunar resources?